This video will explore the luminosities and lifetimes of main sequence stars as a function of stellar mass. 90% of stars are found on the part of the HR diagram known as the main sequence. This is the long, stable part of a star's lifetime, about 90%, when its energy is coming from hydrogen being fused into helium. Many main sequence stars are in binary systems, which allows the determination of their masses. Note that stars on the bottom right of the main sequence are very low-mass red dwarfs, while stars near the upper left are high-mass blue stars. Stellar masses range from 0.08 solar masses to well over 100 solar masses. It is interesting to note the luminosity values for these stars with known masses, which is described by the mass-luminosity relation L equals m to the 3.5 in solar units. Note that this is a rapidly growing function. A 2 solar mass star has a luminosity of over 11 solar luminosities, while a 5 solar mass star has a luminosity of 280 times that of the Sun. So stars have a much greater range of luminosities than masses, ranging from stars with over 1 million solar luminosities down to 1/10,000th of a solar luminosity. Realize that the first step in a nuclear fusion reaction is overcoming the Coulomb barrier, the repulsion due to the positively charged protons. As stellar masses increase, the weight pushes down on the core, creating high pressures, temperatures, and velocities, which allow positively charged nuclei to get close enough to fuse before their like charges repel them apart. Thus, more massive stars have a much higher rate of nuclear fusion, energy production, and thus luminosity. This is memorably depicted in this fun graphic of the HR diagram for cars, where we have plotted the power output of cars on the y-axis increasing upward, and weight on the x-axis increasing to the left. Most stars fall along a main sequence where we get large, powerful cars in the upper left and small, efficient cars in the lower right, just like for stars. Different cars also have radically different rates of fuel consumption. Volkswagen Beetles with 34 miles per gallon in the lower right to Hummers with 9 miles per gallon in the upper left. We can also visualize these concepts with, sparklers. I am going to light a single sparkler, a low-mass star, 3 sparklers arranged in a triangle, a medium-mass star, and a group of 7 sparklers arranged like hexagonal mirror segments representing a massive star. We certainly expect that the 7 sparkler combination will be brighter than the 3 sparklers, which will be brighter than 1. We can also time how long they last. Let's see if you can predict the outcome. Which of the sparkler stars will burn the longest? 1 sparkler, 3 sparklers, or 7 sparklers? Classroom students should follow normal procedures or instructor guidelines. Viewers not in a classroom should record your vote and explain your reasoning on a piece of paper. Please pause this video and answer the question. Let's actually do this experiment and observe the answer. We start with the single sparkler and it goes on like this for 42 seconds. So we bring in the 3 sparkler combination and immediately notice that it is much brighter and it only lasts 22 seconds. We light the 7 sparkler combo using welder's gloves and goggles, and it is actually so much brighter and burns so much faster, it is a little scary. Note that our 7 sparkler star was much more luminous than our 3 sparkler star, which was much more luminous than a single sparkler. Not only is there more stuff to burn for the collections of sparklers, but the proximity of the sparklers keeps temperatures high and makes the burning occur more rapidly. Our single sparkler burns much longer, 42 seconds, than the 3 sparklers, 22 seconds, and the 7 sparklers is very brief, only 16 seconds. Note that it may seem a little counterintuitive that the star with the least mass lives the longest, but it is due to the rate of nuclear reactions. The lowest mass star is like a compact car. It uses its fuel conservatively. Let's derive a relationship for the main sequence lifetime of a star. We start by writing an equation that expresses the total energy a star produces in its entire lifetime, T. This is just a product of luminosity L, the energy a star produces each second, times its lifetime, which here is in seconds. Now realize the star's energy comes from thermonuclear reactions. We are converting some fraction of a star's mass into energy through the equation E equals mc squared. So if we take the fraction f of a star's mass and then convert that into energy, we have this total energy a star produces during its lifetime. Let me solve this equation for t, and you can see that a star's lifetime in seconds equals this fraction f times c squared divided by the mass to the 2.5 power. One trick we can employ here is to divide the equation of a star's lifetime by the same equation for the Sun. The constants will then cancel out, and we will be left with an equation in solar units. Note c squared cancels out easily. I'm assuming that f, the fraction of mass converted into energy in a star's life, is the same for every star. We are left with an equation that says the lifetime of a star is equal to 1 over mass to the 2.5 power in solar units. M is in solar masses, and T is in solar lifetimes, which for each solar lifetime is 10 billion years. So when the mass is big, the lifetime of the star is short, and when the mass is small, the lifetime is very long. More teaching materials can be found on the web at astro.unl.edu.